General relativity, step by step. I've got the Einstein field equations here, which I've been developing over the last few screencasts, and we've pinned them down except for this constant k, which is actually quite a lot of trouble to pin down. It's going to take quite a lot of time to do that. So what I'm going to do is start a long sequence of argument that will pin down the numerical value of k. It's just a scalar, it's just a constant. It's not a function of anything, it's just a constant. And okay, well let's just start by writing out the field equations in their full form. Minus a half Ricci scalar g alpha beta, and that's the Einstein tensor, plus the cosmological constant g alpha beta equals some constant k which we don't know, times the stress energy tensor. Should be a minus there. And I'm going to multiply. What I'm going to do is I'm going to fool around with this equation and I'm going to bring it into an alternative form. So I'm going to multiply by g alpha beta on the left and the right and see what happens. And of course I'll just get r minus a half r g alpha beta plus cosmological constant g alpha beta equals g alpha beta k times t. Sorry, that's a t, isn't it? K t alpha beta. So g alpha beta, you'll remember that the metric tensor is its own inverse, and that's just minus 1 times minus 1 plus 1 squared plus 1 squared plus 1 squared equals 4. So I can rewrite this equation here as r, the Ricci scalar, minus a half times the Ricci scalar times 4 plus 4 cosmological constants equals k times t, where t equals the twice contracted metric tensor, like that. So what does that tell us? Well, by some rather simple arithmetic, we've got r minus 2r plus 4 cosmological constants equals kt. I guess we can simplify that a bit more, equals kt. This is quite an interesting scalar equation that is a direct consequence of the Einstein field equations. So I'm going to stop there and develop this and use this in the next screencast. Stop.